I'm covering the topic of confidence intervals in 5 videos, and this is the first of the 5. This way you won't have too much to learn at one time. Let's suppose we would like to know what the average length is for all of the fish in a huge lake. Would it be practical to take a census? No, because then we would have to catch every fish in the lake. That's not practical. But we could take a random sample of fish from the lake. Suppose we got a random sample of 36 fish from the lake, and the sample mean was 8.25 inches. And for this first video, let's suppose we know the value of the population standard deviation. That sounds pretty absurd, doesn't it? When does one know the value of the population standard deviation when they don't even know the value of the population mean? Don't you need to know the value of the population mean in order to calculate the population standard deviation? Yes, you do. So why am I suggesting we assume to know its value? Is this just my sick idea of a cruel joke on you? All right, here are the 2 reasons why we will be doing it this way. And playing a cruel joke on you is not one of them. First and foremost, this will make it easier for you to learn and understand confidence intervals by not giving you too much to learn all at once. This allows us to postpone the extra new concepts you must learn when I explain what we do when the population standard deviation's value is unknown. It's not until we get to video 4 of our 5 videos that I get to that topic. But you need to learn some fundamental concepts before you get there. And our second reason for this approach, there actually are some situations in the real world where you do know the value of the population standard deviation, but do not know the value of the population mean. But those situations are far outnumbered by the situations where the value of the population standard deviation is not known. Now that we got that out of the way, let's continue. Here's the list of what we know. The sample size n equals 36. The sample mean equals 8.25 inches. And the population standard deviation equals 2.25 inches. Using just this information, what can we determine about the distribution of all the possible sample means that I could ever possibly get? In other words, what do we know about the sampling distribution for the sample mean? And why should I even care about that theoretical concept of a sampling distribution? Hey, that sampling distribution is going to explain everything for us. So if you're a little unsure of what a sampling distribution is, you should probably go back and review it. But here is a quick refresher on it. It's the distribution of all the possible sample means that you could ever possibly get from repeated sampling, hence the name sampling distribution. And even though it would not be practical for you to actually go out and create this, we do know all we need to know about it, thanks to all the theoretical work that some very smart mathematicians have done for us. There are only 3 things we need to know about a distribution in order to use it to answer all of our other questions about it. What are the 3 things we need to know? Perhaps my poetry will help you. Shape, center, and spread. It's all that needs to be said. Shape, center, spread! It's all that needs to be said! The shape of our sampling distribution for the sample mean should be approximately normal since our sample size is large, at least 30. The center is equal to the population mean, and we do not know its value. In fact, that is what we are trying to figure out. The spread we do know thanks to the hard work of those smart mathematicians. It's the population standard deviation divided by the square root of the sample size. It sure was convenient that we just happen to know the value of the population standard deviation, huh? Here's the question that faces us now. Can we use what we do know, the shape and spread of the sampling distribution, in order to get an idea of what the center is equal to? Remember, this center of the sampling distribution is equal to the population mean, which is what we are trying to find. And please don't let it bother you too much that we're claiming to know the value of the population standard deviation. We will handle all of your objections on that topic when we get to video number 4. For now, you just need to grasp what we are covering next. Wherever the population mean is on the number line, all of the possible sample means that we could ever possibly get will cluster around it in an approximately normal distribution. Why? Because their sample sizes of 36 are large, at least 30. When they are this large, the resulting sample means are doing such a good job of estimating the population mean that they will cluster around the population mean. This clustering produces an approximately normal distribution. And normal distributions adhere to the empirical rule, which tells us that the middle 95% of all the possible sample means will be within 2 standard errors from the population mean. Do we know the value of the standard error, which is the spread of our sampling distribution for the sample mean? We sure do! Divide your population standard deviation of 2.25 by the square root of your sample size 36, and you get 0.375 of an inch. How do we interpret this? It's how close we can expect our sample mean to be to its estimate of the population mean. In other words, the typical or standard amount of error we can expect to have when using our sample mean to estimate the population mean. It would be very typical for it to be off by 0.375 of an inch. That's pretty close. Let's look at this middle 95% of all possible sample means that we could possibly get. We know that 95% of the time we will get one of these sample means. That's what the sampling distribution for the sample mean is telling us. Observe the length of this interval that contains the middle 95%. It's approximately 2 standard errors above and 2 standard errors below the population mean. 1.9600 if you want to be more exact, but let's just round off to 2 for now. We are going to use the length of this interval to create our confidence interval. This is how we are going to do it. When we take a random sample and get a sample mean, we will straddle this interval length around the sample mean. So the sample mean will be in the center of the interval. Now here's the big question. Will this interval that's straddled around the sample mean actually contain the population mean in it somewhere? That's what we're hoping for. But will it happen? In order to really understand this next concept, you need to see it animated. So let's do that now. Suppose we get any one of these middle 95% of all possible sample means we could ever possibly get. What happens? The confidence intervals will contain the population mean in it somewhere. So what proportion of the time will we be lucky and get one of these sample means? 95% of the time. Why? Because 95% of all the sample means are within 2 standard errors from the population mean. Now let's consider the possibility of being unlucky and getting misleading results. We could get a sample mean that's more than 2 standard errors above the population mean. What proportion of the time will this happen? 2.5% of the time. See how every one of these results in an interval that does not contain the population mean. Don't you hate it when that happens? But comfort yourself in the knowledge it only happens 2.5% of the time. Now what happens when we get one of the sample means that are more than 2 standard errors below the population mean? See how every one of these results in a bad confidence interval that does not contain the population mean? What proportion of the time does this happen? 2.5% of the time. To sum it all up, what proportion of the time will you be misled by getting a sample mean that is unusually big or unusually small? 5% of the time. Because 2.5% of the time, the sample mean will be too big, and 2.5% of the time, it'll be too small. But 95% of the time, the sample mean will be reasonably close to the population mean, which will result in a confidence interval that does contain the population mean in it somewhere. In the next video, I will show you how to actually calculate this interval. After calculating it, you will then state your answer like this. We are 95% confident that the population mean length of all fish in this lake is between 7.52 and 8.99 inches. Why are we 95% confident? Because 95% of the time, this method will give us an interval that actually contains the population mean. Now you are ready to go to the next movie. Confidence Intervals Part 2, What's in it for you? Don't stop now. Keep going.